Chapter 8, Further Applications of Integration. The Gateway Arc in St. Louis, Missouri, stands 630 feet high and was completed in 1965. The arc was designed by Eero Saarinen using an equation involving the hyperbolic cosine function. In exercise 8.1.42, you are asked to compute the length of the curve that he used. We looked at some applications of integrals in Chapter 6, areas, volumes, work, and average values. Here we explore some of the many other geometric applications of integration, the length of a curve, the area of a surface, as well as quantities of interest in physics, engineering, biology, economics, and statistics. For instance, we will investigate the center of gravity of a plate, the force exerted by water pressure on a dam, the flow of blood from the human heart, and the average time spent on hold during a customer support telephone call. 8.1 Arc length. Sidebar, see figure 1. Back to the text. What do we mean by the length of a curve? We might think of fitting a piece of string to the curve in figure 1 and then measuring the string against the ruler, but that might be difficult to do with much accuracy if we have a complicated curve. We need a precise definition for the length of an arc or a curve in the same spirit as the definitions we developed for the concepts of area and value. If the curve is a polygon, we can easily find its length. We just add the lengths of the line segments that form the polygon. We can use the distance formula to find the distance between the endpoints of each segment. We are going to define the length of a general curve by first approximating it by a polygon and then taking a limit as the number of segments of the polygon is increased. This process is familiar for the case of a circle, where the circumference is the limit of lengths of inscribed polygons. See figure 2, sidebar figure 2. Back to the text. Now suppose that a curve big C is defined by the equation y equals f of x, where f is continuous and x is greater than or equal to a and x is less than or equal to b. We obtain a polygonal approximation to big C by dividing the interval open bracket a and b close bracket into n subintervals with endpoints x sub naught, x sub 1 through x sub n, and equal with delta x. If y sub 1 equals f of x sub I, then the point big P sub I of x sub I and y sub I lies on big C, and the polygon with vertices big P sub naught, big P sub 1 through big P sub n, illustrated in figure 3, is an approximation to big C. See figure 3. Back to the text. The length big L of big C is approximately the length of this polygon, and the approximation gets better as we let n increase. See figure 4, where the arc of the curve between big P sub I minus 1 and big P sub I has been magnified, and approximations with successively smaller values of delta x are shown. Therefore, we define the length of big L of the curve big C with the equation y equals f of x is greater than or equal to a, and x is less than or equal to b, as the limit of the lengths of these inscribed polygons if the limit exists. See figure 4, sidebar. Equation 1. Big L equals the limit as n approaches infinity of the sum from I equals 1 to n of the absolute value of big P sub I minus 1 big P sub I. Notice that the procedure for defining arc length is very similar to the procedure we used for defining area and volume. We divided the curve into a large number of small parts. We then found the approximate length of the small parts and added them. Finally, we took the limit as n approaches infinity. The definition of arc length given by equation 1 is not very convenient for computational purposes, but we can derive an integral formula for big L in the case where f has a continuous derivative. Such a function f is called smooth because a change in x produces a small change in f prime of x. If we let delta y sub I equal y sub I minus y sub, if we let delta y sub I equal y sub I minus y sub I minus 1, then the absolute value of big P sub I minus 1 big P sub I equals the square root of open x sub I minus x sub I minus 1 closed squared plus open y sub I minus y sub I minus 1 closed squared equals the square root of open delta x closed squared plus open delta y sub I closed squared. By applying the mean value theorem to f on the interval open bracket x sub I minus 1 and x sub I close bracket, we find that there is a number x star sub I between x sub I minus 1 and x sub I such that f of x sub I minus f of x sub I minus 1 equals f prime of x star sub I times open x sub I minus x sub I minus 1 close. That is, delta y sub I equals f prime of x star sub I times delta x. Thus we have the absolute value of big P sub I minus 1 big P sub I equals the square root of open delta x close squared plus open delta y sub I close squared equals the square root of open delta x close squared plus open bracket f prime of x star sub I delta x close bracket squared equals the square root of 1 plus open bracket f prime of x star sub I close bracket squared square root of open delta x close squared equals the square root of 1 plus open bracket f prime of x star sub I close bracket squared delta x, since delta x is greater than 0. Therefore, by definition, 1 big L equals the limit as n approaches infinity of the sum from I equals 1 to n of the absolute value of big P sub I minus 1 times big P equals the limit as n approaches infinity of the sum from I equals 1 to n of the square root of 1 plus open bracket f prime of x star sub I close bracket squared delta x. We recognize this expression as being equal to the integral from a to b of the square root of 1 plus open bracket f prime of x close bracket squared dx. By the definition of a definite integral, we know that this integral exists because the function g of x equals the square root of 1 plus open bracket f prime of x close bracket squared is continuous. Thus, we have proved the following theorem. Equation 2. The arc length formula, if f prime is continuous on open bracket a and b close bracket, then the length of the curve y equals f of x, and x is greater than or equal to a but less than or equal to b, is big L equals the integral from a to b times the square root of 1 plus open bracket f prime of x close bracket squared dx. If we use the Leibniz notation for derivatives, we can write the arc length formula as follows. Equation 3, big L equals the integral from a to b times the square root of 1 plus open dy over dx close squared dx.